As it happens with the full implicit method, the matrix representation for the Crank-Nicholson method is going to be extraordinarily useful in order to apply this finite difference method. So this is the finite difference representation we got for the Crank-Nicholson method. So we have like n is running from 1 to nx minus 1. So we have like nx minus 1 equations like this one. We have to apply for all different j times. The alpha values, as usual, is this one. And it's very useful to have a matrix representation. So all these equations appear in just in one picture, which is the matrix itself. So I don't need to go into detail. The thing here is that because actually we can follow the same strategy than the one we followed for the full implicit method. Here it's a bit more, let's say, complicated because it's the equation, it's longer, let's say. So we're going to have a matrix representation here of the left-hand side of the equation, and we are going to have another one for the right-hand side of the equation. So here first we have the one corresponding here to left, which is the one, which again, everything here depends on j plus 1. Everything we have on the left will depend on j plus 1, and everything on the right is going to depend just on j. So that's the finite difference this is the matrix representation we have for this equation. This is the left-hand side of the equation. This is the one. So I'm not going into detail, but it's very easy to check that this is the one. So basically you can apply that equation for n equal 1, and you'll see that this is the corresponding one. Again, you can see that this matrix here is not a square matrix. It has these dimensions here. Okay, so this is the one corresponding to the left, and then we have, this is the one corresponding to the right. Okay, this is the one corresponding to the right. So again, everything goes the same. So remember, this matrix didn't appear in the case in the full implicit method. You just had the other part, even though it's a little bit different. So that's the matrix representation. And again, here in these methods, again, have nx minus 1 rows and nx plus 1 column. So the same thing we said about in the full implicit method. So that's a representation of the nx minus 1 equations, and we have, as we know, nx plus 1 unknowns. So the two equations that we are missing, again, are related with the boundary conditions. So using the conditions, we are going to convert, as it happened with the full implicit method, this system of equations into a system of equations involving square matrix. That's going to be important in order to clear the values of the u functions evaluated at time j plus 1. So the aim again is to write the system of equations and the matrix representation we have seen before in this way, where again we have that should be a matrix, square matrices. These should be square matrices. This one is multiplying the u vector evaluated at j plus 1. The other one is multiplying the u vector evaluated at time j. And you can have also, depending on the kind of boundary conditions we have, you can have another column vector, one evaluated here at j plus 1, other one evaluated at time j. So as you can see here, the vectors and these vectors and the matrices appearing on the left, which are related with the j plus 1 time. We have a upper script here with L indicating that they are in the left-hand side of the equation, and the other ones, which correspond to time j and appear in the right-hand side of the equation, they are going to have an upscript R corresponding to the right-hand side of the equations. So again, so later our aim here is how to build these two matrices, two square matrices, and these two vectors, as well as using the matrix representations we have just seen. So the basic difference with respect to the fully implicit method here is that we have two m vectors and two r vectors here. But the strategy in order to get both of them is the same, actually, the one we already explained for the fully implicit method. But we'll still have a look to this equation in order to show the expression for these two m matrices and two r vectors.